Well, I have the pleasure or the honor to be the last speaker today. I have prepared a bit hardcore mathematical lecture, geometrical and no historical information, but perhaps I will say without some remarks. So we owe this conference, I believe, to Plato, because someone mentioned Plato. So in one of his dialogues, he said that the world was created according to form and number, and form is nothing like geometry. So all this conference, geometrical study of the universe, is more or less due to some remark of Plato. So, and another, as you see here, I come from Jagiellonian University, which is a bit far from here, but in the Middle Ages, there was a university in Krakow, and still is, fortunately, and we have the second chair in mathematics in Europe. One of the burghers of Krakow had a fancy idea to found a chair in mathematics, astronomy, and astrology. It was in 1405. So, well, I can tell you, I'm not sure whether you agree with me, but astrology is just a very fine scientific theory with just one mistake. And I will leave you to guess what is the mistake in this fine scientific theory, which is many current, let's say, theories have more mistakes than one, I would say. So anyway, the universities, as they were created, starting from the 13th century, you see, taught a lot of mathematics, because quadrivium was based on the ideas of Plato. As you know, to the academy, Platonian academy, no one who was not fluent in geometry could pass this threshold leading to this academy. So let's say, I can say, I wonder how many students we'll have at the university if we apply this rule to present, you see, pupils. I wonder, just wonder. So after this historical information, I will start with my lecture. So you see, it's a joint research with Rosbeh Mohseni, who graduated in physics, and he came from Isfahan to Krakow, and he somehow, you see, talked to me, and I decided to introduce him to foliations. I'm a great fan of foliations. I try to foliate everything, including I foliated perverse forms, if you know in which part of mathematics they are used. Well, so we started to foliate Twistor spaces. So let's go. So the subject is Twistor spaces on foliated manifolds. Okay, so it's I prepared to see 5 parts. So I will introduce some formal definitions about foliations, then twistors on foliated manifolds. Let's say we'll look at the transverse twistors, tangent twistors, and mix together these twistors, and then you see 3 parts are about applications, geometrical applications. I mean harmonic mappings, cohomology of special manifolds, including, let's say, I talk here. The talk is about, you see, a so-called Hart-Lefschetz theorem about Hart-Lefschetz property, which is well known for Keller manifolds, and it could be foliated. So it's for transversely Keller foliations, and there is a version for quaternonic manifolds. let's call it Kreiner theorem. So it also could be foliated, and the Twistor come in this part because using the space of the quaternionic manifold, the Twistor space of a quaternionic manifold is a Keller manifold, so we can, use it. And of course, the foliation theory is very useful in the study of orbifolds. And you know that in physics some orbifolds are used. So let's say this section 1, Twistors, generalized Twistor. So I will just skip it quickly. Let's say, so it's a bundle. Twistor space is a parameter space of compatible, almost complex structures, compatible with a fixed Riemannian metric. So it's a bundle with a very special fiber. And what is important, we have two almost complex structures which are very useful. One of them is integrable, the other is never integrable. So there's a generalization. There are so-called Twistor fibrations, and they are used that mapping into the Twistor space when projected to the base space is harmonic. So it's a way rings between harmonic mappings and holomorphic mappings. So what about foliation? It's a standard definition, classical, one of the classical definitions using a cocycle. So we have an open covering of a manifold, local submersions with connected fibers, and in the target space, this Fi, you see the target space are, of course, very small in many ways. And what is important is that because fibers should glue together to form a submanifold, so these, you see, we have this local diffeomorphism, Kij, and you see the third condition is this gluing condition. So that's why it's called cocycle, because Kij composed with Kjl gives you Kil. So it's a cocycle condition. So a lot of actually what is important, many speakers, you see, talked about transverse structures. Actually, transverse structures of a foliation is just, you see, can be read on the level of these images of Kij's, like that here. So we can here, you have here a tangent space and the normal bundle, which is the quotient bundle of Tm and Tf. Tf is a tangent bundle. So of course, it's an abstract bundle. So what is important is that we very often use the embedding of this abstract bundle into the manifold. So we have the splitting of the tangent bundle into the tangent bundle to the manifold, into the tangent bundle to the leaves, and this transverse part. Or in the Riemannian case is just the orthogonal complement. So we can define any structure, any Riemannian structure you can imagine, more or less. We can use the normal bundle to define these structures. Is, for instance, transversely Hermitian. We have transversal Keller, whatever you can imagine. Most you can do it transversely. And what is important, this normal bundle, this Q can be foliated. So it has a natural foliation whose leaves are of the same dimension as the initial foliation of the manifold M. And the leaves are covering spaces, covering manifolds of the leaves of the initial foliation. So what else? So we have here, you can have I will just skip it. So let's go to the Twistor spaces, which is the subject of my talk. So we introduce normal twistors or transverse twistor, normal twistors, because here we use the normal bundles. So we have the space of the compatible complex structures, almost complex structures, ZMF. And the union of these fibers is a bundle. And you see this bundle is ZMF, and we can apply the same construction to the normal, to the manifold, to this transverse manifold N. And because we have the QX is linearly isomorphic with the corresponding tangent space of the normal manifold, these two spaces, the spaces of compatible complex structures are isomorphic or can be identified. It means that the twistors, the normal twistor bundle ZMF admits a foliation of the same dimension whose leaves are of the same dimension as the initial foliation F. So this procedure, of constructing, you see, foliated and transverse geometrical structures are more or less, you see, can be repeated in this case. So you have here in the last line, you see that ZMF I is isomorphic to this restriction of ZMF of the normal twistors when restricted to UI. The same UI from the cocycle is isomorphic to the pullback of Zn of the twistor space of the normal of the transverse manifold N. So it means that on ZMF we have a cocycle, a foliate which defines a foliation of this manifold. So on a foliated manifold we have the splitting. I repeat, Tm can be identified with this direct sum of the tangent bundle to the leaves L and the normal bundle. So we can consider almost complex structures on Tm which preserve the splitting. This J of L goes to L. So we have here, we can define tangent twistors. We had normal twistors and tangent twistors. So we denote by ZF the bundle. So we have on a foliated manifold, a Riemannian foliated manifold, we have different spaces as the twistor space of the manifold itself, the bundle of normal twistors and the bundle of tangent twistors. So we can take the fiber product, and the fiber product can be embedded into Zm. And that's the base of some results. You see? So let's say that's the technicalities, which I can skip it. Well, how much time have I got?
10 minutes.
10 minutes, oh, I'm quite quick. Okay, so we can applications, so we can have applications on, let's say, when we have two foliated Riemannian manifolds with a transverse almost complex structures in the normal bundle JQ on F and JQ prime on M prime, we can have a transversal holomorphic mapping. It means a mapping which is foliated, leaf preserving, means that the differential sends vector tangent to leaves to vector tangent to leaves of the other manifold. And it's called transversal holomorphic when the differential commutes when the differential, you see, when the mapping induced on the transverse on the normal bundle commutes with the you see with these almost holomorphic structures or holomorphic structures on the normal bundles, on the corresponding normal bundles. Okay. Sorry. That's it. So we can define for Riemannian foliation, we can define transverse tension field. So here we have normal bundle, we have orthonormal frame, base frame, we have the Levi-Civita connection induced on the normal bundle Q, and of course we can define the trace, etc. We just mimic the standard construction of the tension field, and you see we see that it's foliated. That what is interesting, very fine in let's say foliation theory, when you have a good construction, in many ways you see can be foliated. It means that it's when a local isomorphism of the structure preserve some object, then this object can be lifted to a, you start with the transverse manifold, and these you see transformations, which I denoted Kij at the beginning, when the object on the standard manifold is preserved by these isomorphisms, then it can be lifted to a foliated object, and a foliated object is more or less, intuitively speaking, constant along the leaves, so it could be projected. So a lot of results which are well known or standard for submersions can be generalized to foliated manifolds. So in particular, this you see harmonic theory of harmonic mappings can be you see generalized to foliated harmonic mappings. So it's here. So you have here the definition: transversal harmonic mapping. If a foliated mapping is transversal harmonic, if its transverse tensile field vanishes. Okay, so you have all this. You see, I can skip it. There are a lot of results here, but it's too short lecture. So cohomology. So there is a cohomology for the cohomology quaternionic manifolds. One can also it is useful, especially in some perhaps I will come to it later, but let me see. Is the last, perhaps I have just enough time. Okay. So okay. So there is a quaternion Keller manifold if there exists an open covering such that there are two almost complex structures on it in IU that are G, the initial metric is Hermitian. These structures commute, and the Levi-Civita derivatives of our structures are linear combinations and of I and J and K, which is the composition. You see, and we have the space of the endomorphism generated by I, J, and K is the same for all I and j, small r and j. So more or less, we have locally these three almost complex structures, which when we pass from one open subset to another, they do not differ a lot. They are just linear combinations of the other structures on the second open subset. So it could be defined in many ways. You see that as a three-dimensional subspace of the suitable homomorphism space of the tangent bundle. So you see, we can define, using this you see, structures, we define, you see, is a Riemannian structure defines a star product, Hodge product. You see, so it's a K form sends to 2n minus k forms, to forms of the complementary degree. Using these structures, we can define a 4 form, capital omega, and we define L, which is multiplication, and lambda, capital lambda, just lowers degree by 4, and it is defined in this way. So it's a nice application. So when you have a foliation which is transversely quaternionic, you see, then all these, you see, it means Riemannian foliations, and in this place, instead of forms on the manifold, you use basic forms. It means more or less forms which are constant along the leaves, and both, and its differential is also constant along the leaves. In the case of submersions, it means that these forms, basic forms, are the forms from the base of the submersions. That's why they are called basic forms. And of course, because condition for the basic is just not linked actually to a submersion, can be generalized for a foliation. This definition is used commonly on foliated manifolds. Okay, so we have effective forms, and we have such a decomposition for the quaternionic Keller manifolds that any differential form can be written in this nice ways using effective forms. And okay, so it's if anyone is interesting, I would be very happy to provide the slides, because okay, so this theorem previous can be generalized for let's say foliated Riemannian foliated manifolds. So you have a similar decomposition. You see, both are simply very similar. So it's a very nice example of a theory which can be foliated, and that's the result of this procedure of foliated. So we have a it means we have something for Betti numbers, a result for the transversal quaternionic Keller foliation. We have Betti numbers related with the basic cohomology. So there is another theorem which can be cheaply generalized, whatever it means. And what is here important that this theorem of the type Hard-Lefschetz theorem for quaternionic, that this linear map, it means multiplication by this capital omega is injective for small k's. K is smaller than q, where 4q is the codimension of the manifold. So it's also a generalization of a theorem for quaternionic manifolds. This time you see using basic cohomology. Okay, and what is interesting is that there are other theorems, like here, in this Fujiki paper, there's a generalization of the so-called cryness in Fujiki papers, but in the standard case, we use the fact that the Twistor bundle is a compact Kähler manifold, and that the pullback to the Twistor space from the base to the total of the Twistor space is injection or injective in the cohomology of the, you see, from the base to the total space. And unfortunately, for transversely quaternionic foliations, even for compact manifolds, the first is true, that the, in some cases, it's true that the total space is transversal Kähler, but the main problems comes with the second property. We cannot simply, you see, mimic, even you see, using all this stuff, we could generalize all the work about basic cohomology. So there's no injection from the basic cohomology of the base into the basic cohomology of the total space of the transverse of the Twistor space, normal Twistor space. So that's a problem because the foliation, both foliations are closely linked, but unfortunately we have no Leray-Hirsch theorem for basic cohomology. Only.
You have to conclude.
Okay, so that's it, and I can only end one remark about orbifold. Why the foliations are useful in the study of orbifolds? Because any orbifolds can be represented as a leaf space of a Riemannian foliation. So all the theorems, or most of the theorems about basic cohomology or basic foliated properties of Riemannian foliations translates immediately into the orbifold properties, and vice versa. Orbifold properties, you see, there are some links between this one. So that's all. Thank you for your attention.
We have just one question. I have a question. For statistical manifold, we have Hessian structures. What could be applied for your models for statistical manifold?
Well, there is a problem. The classical theory works only for regular foliations. So, and the theory of singular foliations, it's not so well developed. So, of course, for Riemannian singular foliations, you have stratification, and one can work strata by strata on each stratum, but to put it together, it's a hard work. So and anyway, that's the place where perverse forms appear.
Okay, thank you.